Okay, so now time for the law of refraction. In the PowerPoint, it talks about the Michelson-Morley experiment and measuring the speed of light. You could look up that and how it involves refraction. It's kind of an interesting idea. It was a failure because they thought there was this ether that light travels through, and but that doesn't exist, right? It was actually a vacuum. So law of refraction. So you're going to find on the PowerPoint tables that sort of look like this. And these are called index of refraction. You'll notice there are no units associated with them, and I'll get into that in a little bit. But you'll also see that air is 1, basically 1, and a vacuum is perfectly 1. So the higher the number, the slower light travels, okay? And so refraction is basically when light slows down or speeds up. If it's coming out of one substance to another, it's going to bend. So I always start out by standing up on a table, and let's imagine you're in a boat, and that's my table. There we are. I don't know what kind of boat that is. Banana maybe? A banana boat? We'll put a little thing up here so I could stand on it. And I'm holding a spear with some big, huge spearhead on it. That's as big as my whole body. All right. And I'm going to try to hit a fish. Okay. And so the question is, if I'm going to stab this fish, that is a terrible drawing. Jeez. If I'm going to stab the fish, where do I aim? Okay. So I'm going to draw my fish like this. Do I aim right where I see it? Do I aim down here, or do I aim above it? Okay. And the fact is, light travels slower in water than it does in air. So when light comes from the fish, so light's reflected off the fish, and it's bounced here, it's refracted out of the water, where is the fish really at? Okay? And a student one time, it was like probably 8 years into teaching, 7 years, she's like, out loud, she goes, that's called gigging. I think it's G-I-G-G-I-N-G when you're stabbing a fish with a spear. So I'm just going to draw it like this. I'm going to draw my surface. I'm going to draw an eyeball up here. Used to make me like basically get watery eyes and eyeball drawn like that in college when I'd see this professor do it. And I'm going to draw my fish. So where's the fish? Here's my line of sight. Here. The fish is actually, I'm going to do this. I'm going to draw the line all the way through. The fish is actually here. Okay. So up here, you would actually aim below where you think the fish is at to hit it. Okay. So the light would actually come from the fish like this and go this way to the eyeball. All right. So a couple things, and I already said this. Light always travels slower in a medium, meaning a substance, than a vacuum. All right. Refraction is when light travels through a barrier. So if we have water and we have air, that would be a barrier. Don't think of a barrier as always having to be like a concrete wall. Okay. It's just where two different substances meet. Okay. And most of the time, what's going to happen is we're going to get a little bit of reflection. Like here's our light coming off the fish. We're going to get some refraction, and then we're also going to get reflection at the same exact time. Okay? Most of the time that occurs. Now, there are certain situations where it just doesn't. And that's going to be called total internal reflection. All right. Looking at my notes right here. So first off, law of reflection. We call N the index of refraction. The higher the N, the slower light travels, the more it bends, okay, when it goes from a high index to a low index, or vice versa. Okay, index of refraction. There are no units. So actually, it is a ratio of C to V. So this is the speed of light in a vacuum, I spelled that wrong, 1 C2Us. And that would be 3.00 times 10 to the 8th meters per second, which is extremely fast. It's about, I think it's 7.2 or 7.3 times around the Earth in 1 second. And this right here is the velocity in a medium or substance. Okay? So light always travels slower in a substance. So if we think about bigger number, smaller number, n is going to be greater than 1. If you ever have an n that's less than 1, it's just wrong. You probably have the numbers flipped. So that's our first equation, determining the index of refraction. All right? I'm going to show this here because I just don't want to write it. All right? So light bends towards the normal. This is not supposed to be a negative sign. Okay? That's like a bullet point. Light bends towards the normal when it goes from a lower index to a higher index. Okay? And then light bends away from the normal when it goes from a high index to a low index. Okay? So let's go back to our fish idea, which is drawn pretty poorly. Here's where the normal is going to be. My surface is here. My normal is perpendicular to the surface. Okay. This right here, depends how we look at it, okay? Depends how we look at it. But n here, we can call air. So it's just basically 1. Down here, we'll say we could call n water, which is basically 1.33. I think it's 1.333. So when we go from a high to a low, it bends away from the normal, meaning this angle is greater than this. If we think about light going from our eye to our fish, so from a low to a high, it bends towards the normal, okay? So we would actually think the fish is over here, but really the fish should be down here. Not my greatest way of showing it. It's a lot easier to do it in class, all right? But when you go from low to high, towards the normal. When you go from high to low, away from the normal. A lot of times this is the way you're going to see it written, okay? You'll see something like N1 is less than N2. So it means the light's going to go like this, down, okay? So let's draw our first one here. Let's draw our normal here, 90 degrees to the surface. And we'll draw our refracted angle here, okay? So let's imagine our light's going like this. This would be defined as theta I. Once again, angle of incidence. Okay. And this right here would be theta R. So it's our angle of refraction. So some students will say, well, why did you pick this as being theta I and theta R? In your other picture, you kind of flip-flopped them. That's fine. That's fine. It doesn't matter. If we call this theta I, obviously that would be theta R then. It does not matter. Our formula is actually called, our equation is called Snell's law. So it's basically N1 sine of theta 1 equals N2 sine of theta 2. So see, it doesn't really matter which one we call like 1 and 2, right? This could be theta 1, N1. This could be theta 2. We would just call that N2 then. We just have to make sure that the index goes with the correct angle. All right. Now you notice here I used 1s and 2s. You could use I's and R's. It does not matter. Like I said, correct end with correct angle. Okay, so basically here you're always going to have three things. You're probably going to have both indexes, and then you'd be looking for one of the angles, okay? Or you could have both angles and one index, and you're looking for one of the indexes of refraction. Okay. So a student asked me, maybe second or third year teaching, kind of caught me off guard. He said, you know, why is it when we're driving down the road on a hot day, you see like the road like look all wavy? And I thought about it. And so here's my answer. It's really good. It deals with both reflection and also the index of refraction, okay? So light obviously is coming down, striking the road, and bouncing towards your eye. That's reflection. Now, if you think about it, the air above the road is going to be heated. When that air changes density, okay, it's going to have a different index of refraction, right? Think about water versus air, different densities, okay? Now, if you heat up air, it's going to be less dense. So once again, that should affect the index of refraction. Also think about, the air above that ground is not going to be all heated up the same. So you're going to have different densities of air creating different bendings, okay, which would cause this kind of waviness. But I think that's the best way to look at that sort of question. It also brings up this idea of having the same substance, but yet a little different density, and how it would affect things differently. Okay. So one of the things that happens, and I ask students to think about this, have you ever gone to a bottom of a pool and looked up? Okay. I don't like swimming. I can recall being pretty young and doing this. And so let's imagine we are here and looking into the paper is looking up. You'll probably notice something that sort of looks like this, right? You could try doing this during the summer. Just don't stay down there too long. So here we are, heads up here, looking out. And what you'll probably see is you'll see the clouds. Oh, how nice. You know, that's great. You might see the sun. We'll put a smiley face on it right now. It's sunny outside right now. Okay. But then you're going to start noticing something over here, and it's going to be all wavy and stuff. Over here, you might see the side of the pool, like underwater. Or you might see the bottom of the pool. Okay? So what's going on? Extremely important in today's society, this idea. Okay, it's called total internal reflection. So here's my water. Here's like the opening where I see the actual sun. Here's my eyeball down here, scary as it may be. Okay. And so light coming from the bottom of the pool. Here's the bottom of the pool. Maybe we have like a little starfish or something down there on the bottom of the pool. I don't know. But basically, as this comes over further and it's reflecting light, all of it, or some of it, but all of it would be being reflected back to your eye. That's one way to look at it. It's kind of a difficult thing to set up. So like water or light's basically getting into the water, but not getting out of the water. Okay. So I shouldn't say this. Actually, I only bought one engagement ring. Yeah, but anyway, I didn't buy the other one. It was a mother's, and I gave it back. But anyway, if we have a diamond, light comes in through the diamond, strikes, bounces, comes back out. This is called the table, if you didn't know that. And this right here is called total internal reflection. It's ideal in a diamond if you want it to be sparkly. So whatever light comes in is bounced around and then shot back out. Now, sometimes if the light hits at a certain angle, you may have some of it refracted out, and then others, other parts of that light would then be bounced around in, and some would come out and some wouldn't. They'd be refracted out to the side. The ideal situation is to have this stuff totally internally reflected so that it comes all back out and it's sparkly to the eye. Extremely important idea when we talk about communications these days: fiber optic cable. Probably 2 words or 1 word. Okay. So fiber optic cable, N1, and on the outside, N2. All right. Basically what happens in fiber optic cable is all of the light is kept inside the cable. And light travels the speed of light, right? Obviously. So in the cable, that light's basically going to be traveling 3 times 10 to the 8th meters per second. If you didn't know this, when you use your cell phone, and I'm sure this is still working the same way, those radio waves or go out to a tower. Some people think they're shot off to a satellite and then beam back down. Your transmissions end up going through fiber optic cables, even like our television transmissions. Okay, fiber optic cables are laid across all the oceans, okay, underneath the water. And it was actually done quite a long time ago. There's like a shelf in the Atlantic Ocean that actually they set the fiber optic cable on so it doesn't have to go all the way down to the bottom of the floor. There's basically like a raised up area that goes between the 2 continents, which is kind of crazy to think about. Okay, so total internal reflection: when all the light is reflected off a surface or boundary and none is refracted out. Okay, if this cable would start to get like roughened up, you would have some refraction out, and that would be a bad thing. Okay, so this happens when you move from a medium of higher index to a medium of lower. So once again, our N1 is going to be greater than our N2. Okay, in class and in physics classes, they'll have like maybe like something like this, and they'll shine a laser light in one side, and then you'll see it come out the other. So basically the laser's bounced all around, then comes out the end. Right? But it only could occur when we go from a high index to a low index. So if you notice here in my water is higher, 1.33 compared to air, 1. We could have that. All right? Now here is my PowerPoint. See if we can see it. I think we can. Here's my talking about a diamond, and I bought an ideal cut diamond for Amanda. Ideal cut diamonds have the most internal reflection, total internal reflection. And then you could see this down here. Okay, there's a point where if we were to shine a light straight up in water, it would go right out of the water into the air. As we do this, it bends coming out, bends coming out, bends coming out, and then we get to this angle that's called the critical angle. Okay, let's draw it down here. So here's my light coming out, goes straight this way, goes a little this way, goes a little more this way. There's an angle that you'll get to where the light ray will bounce straight down the barrier. If we tilt more than that, that is when it begins to be reflected back in. Okay, the point at which the light bends straight down the barrier is called the critical angle. Okay, so here is that. This would be called theta C, or the critical angle. Okay. So how would we get that critical angle? Okay, which we'll call theta C, theta R, whatever you want it to be. Okay, critical angle. It's when theta R, or the refracted ray, is equal to 90 degrees. So see, this is our incident ray, theta I, theta C, whatever you want to call it. And this right here is our refracted ray. So it's going 90 degrees. So basically we have N1 sine of theta 1 equals n2 sine of theta 2. n1 is going to be our high index, like 1.33. n2 is going to be our like 1, okay, for air. And so this, for our critical angle, would be 90 degrees. So what is sine of 90 degrees? It's 1. So this whole thing is 1. So if I want to figure out what angle, this one right here, would produce this critical angle or would produce an angle at which the light would totally be reflected, we can just solve here. So, okay, where n1 is greater than n2. I always like to go back and check. See here are my notes. I obviously took the sign out and put it over on the other side. So theta 1, this right here, label it what you want, theta 1, theta c for critical angle. This would be our critical angle. All right, so that's it for refraction. I'll do another video actually going over the example problems, and I think it'll make more sense when we actually start to do the example problems and how light bends and how we solve for it. Nice thing, one formula, one equation. That's it.